Hello there. Welcome to Moody Institute of Science. Say, do you like mystery stories? Well, we have one for you. In the tradition of all good mysteries, it's complete with a haunted house and ghosts out of the past. A science lab seems a strange place to look for ghosts, doesn't it? But our story is true. Before we're finished, I think you'll agree that truth is stranger than the strangest fiction. The mystery is time. The haunted house is space. In our true story, the ghosts travel at the speed of light, and they come straight out of the past. Your past. Yes, time is a mysterious thing. Have you ever tried to define time? The harder you search for a definition, the more elusive it becomes. We're going to explore the mystery of time in the laboratory. Before we find the ghosts, we'll have to sort through some facts, but we'll find them, for they're very real. Hello, Pete. How are things going?
Fine, Dr. Moon. We're about ready to roll on a high-speed shot.
Oh, that's great. Mr. Margosian is one of our skilled technicians here at Moody Institute of Science. In addition to a rich background of photographic experience, he's shown a more than usual interest in the subject of time. Pete, do you suppose you could tell us just a bit about the equipment that you used?
I'd be glad to. The most important piece of equipment is right here. It's a super high-speed camera. I like to call it a time microscope. It does to time what the microscope does to physical dimension. It enlarges a period of time instead of a bit of matter.
How fast will the camera be running on this tape, Pete?
About 3,000 frames per second.
Let's see. That'll stretch 1 second into about 2 minutes, won't it?
Yes, 2 minutes and 5 seconds to be exact. And this will give us an opportunity to observe some interesting properties in liquids. We're using milk in this experiment because it photographs easily. I'll adjust the flow until it appears a fine trickle to the eye. There. Would you start the camera, Doctor?
Now?
Ready?
The trickle of milk and the splash look quite different now, don't they? But they aren't any different. The liquid is behaving in its usual manner. We've merely changed our time reference. Did you ever drop a steel ball into a bowl of milk? There's probably no good reason why you should have, but it does make an interesting high-speed study. Watch. The high-speed camera checks the fall, and the steel ball seems to float slowly downward to disappear beneath the surface of the liquid. Then, when you've almost forgotten about it, the ball slowly bounces back. Don't be confused now. This isn't one of the ghosts we were talking about. It's just the milk that follows the ball into the air. You never question what appears to be normal as one sure way of staying locked up in your time compartment. To study time, we must venture beyond the ordinary. And when we do, it opens up a whole new realm. Pete, would you help me with an experiment?
Sure.
Just take the egg and stand right over there. That's fine. Now, will you balance the egg on your head, please?
Hey, wait a minute. If you have in mind what I think you do, no thanks. But I'll be happy to set it up over here for you.
Well, maybe that would be safer, Pete. You know, if William Tell had been in the chicken business instead of the apple business, the story might have gone something like this. Of course, the flight of that arrow required but a tiny fraction of a second. But the high-speed camera slowed it down until we could study the entire action. Recently at the University of California at Los Angeles, a high-speed camera study was made of that split second involved in a head-on auto crash. That's what happens when we crack up at only 28 miles an hour. Not many of us keep it down to that anymore, do we? It's a bit disconcerting to realize that just a fleeting moment of this stuff we call time can introduce you to a whole eternity. The high-speed camera tells us part of the story of time. But strangely enough, the time compressor will show us even more. The time-lapse camera, or the time compressor, is just the opposite of a high-speed camera. Instead of slowing things down, it speeds them up. The world about us is alive with action and movement that we miss because it's too slow. There's a veritable symphony of movement that we never see because we're locked up in our own little time compartment. The time compressor can help us break out of our time prison. Here's a good example of movement that we can't see. Let's set the clock now for 11 o'clock. Right, the clock is running. The hands are moving all the time. You can't see them move. Oh, if you watched long enough, you could tell that they had moved, but you can't see the movement. That is, not unless we use the time compressor. Did it seem to you that the hands of the clock speeded up and slowed down? Well, actually, they didn't change speed at all. The clock kept right on running at standard clock speed. You've been watching it for a whole day. Now, we just changed your time reference by changing the interval like this. Every time the lights go on, the camera takes one picture. If you're still not convinced about that clock, maybe this will help. That isn't a magician's rose. It's a flower right out of the garden. This time, you watch the clock and the rose. We are now taking pictures at a 10-minute interval. Of course, we're projecting them at standard sound speed. This means that we are compressing 72 hours into just 18 seconds. Yes, this is a real rose. And these are real whiskers, too. You see, I haven't shaved since you started to watch that rosebud open 3 days and nights ago. Gives you something to think about, doesn't it? This is a 3-foot length of standard 16-millimeter motion picture film. On it, there are 120 separate pictures. This 3 feet of film could go through the high-speed camera in a... Oh, I shaved while you were looking at the close-up of the film. You see, we used the time-lapse camera to take the close-up, so there was plenty of time. This 3 feet of film could go through the high-speed camera in 1,000th of a second. The same length of film in the time-lapse camera could take days, months, or even years to expose, according to the interval that we used between exposures. I suppose that we could call a piece of film like this a memory with a variable time reference. Say, would you like to take a nice 2-day vacation? All right, sit back, relax, and enjoy yourself. A number of years ago in Germany, a man gave to the world a new concept. It shook the scientific world from top to bottom, changed the course of human history, and gave us the atomic age. The man, Albert Einstein. The concept, relativity. That strange, fantastic relationship between time, distance, and mass. Now, an important part of that concept can be expressed in a simple equation. E equals mc squared. Energy equals mass times the speed of light squared. The equivalence of mass and energy. The basic formula that unlocked the secrets of the atom. But equally, if not more important, is that relationship between time and space. Now, we can't speak of the equivalence of time and space. They're not exactly equal. But we can say that they are relative, for they are all bound up together. Just obtuse theory, you say? Well, maybe so. But every day there is new concrete evidence to prove it true. When Dr. E.O. Lawrence and his associates at the University of California designed the 184-inch cyclotron, they didn't laugh at this theory. They accepted it as true, and it's a good thing they did. In the cyclotron, tiny particles are accelerated in magnetic and electrical fields until they approach the speed of light. This rotary condenser at the side of the cyclotron compensates for the increased mass of the particles, which occurred exactly as Einstein had predicted it would. Let's suppose that at some day in the Buck Rogers future, you decide to take a trip to a planet satellite of the star Sirius. As long as we're supposing, let's say that your atom-powered rocket ship is capable of traveling at 99 and 99,999,999 100 millionth% of the speed of light. Now, of course, this is very close to 186,284 miles a second. In view of the fact that Sirius is 9 light years from the Earth, it would take just a little over 18 years to make the round trip. Naturally, you'd plan to take a large supply of food, but all you'd need would be a sack lunch. Traveling at this speed, not only would your watch slow down by a factor of 70,000, but your heart, respiration, digestion, appetite, all would slow down in the same ratio. You could leave the Earth some morning right after breakfast. By the time you got to Sirius, you'd be ready for a sandwich. And when you got back to the Earth, you'd be just hungry enough for a good dinner. But then would come the surprise. You'd find that while you were only 1 day older physically, your children would all be grown up and through college, and all your friends would be 18 years older than when you left them just 12 hours ago by your watch. A concept such as this is almost impossible for the human mind to grasp. It's so far beyond our normal experience. But maybe this will help. First of all, listen to my heart. Now, let me start the clock so that you can become accustomed to the rhythm of its beat. The yardstick. It looks normal, doesn't it? But if we could accelerate this room and everything in it to the speed of light, 186,284 miles a second, time would stand still. My heart would stop beating, yet I wouldn't die. The clock would cease to run. And everything would squeeze into a line, infinitely thin. Now, we can't speed the room up to the speed of light, of course. But with the magic of some very special photography, we can show you exactly what would happen if we could speed up the room to 90% of the speed of light, 167,000 miles per second. Are you ready? All right. There's our speedometer. And we're going to travel in that direction. You notice what's happening?
My voice is changing. Look at the clock. Listen to my heart. Let's go back to normal now.
This time, we're going to accelerate vertically instead of horizontally.
Now the yardstick is 18 inches long, approximately when we hold it vertically. Then it comes back to 36 inches
when we bring it to the horizontal. When the room was accelerated, everything seemed normal to me. My voice sounded the same. The rhythm of the clock remained constant. The yardstick seemed the same in both directions. That's because I was accelerated along with the room. But you, as a stationary observer, were aware of the changes. Now, of course, the visual effects which you noticed were achieved in this case by the use of a Panavision lens, a variable aspect ratio lens. But the effect was exactly the same as if the room had actually been accelerated to 90% of the speed of light. These are called relativistic effects. They are based on mathematical formulas that are as common in the workaday world of the nuclear physicist as 2 times 2 equals 4 is in our world. Fantastic as they may seem, these are the formulas that gave us this. The knowledge we've been discussing created a Frankenstein monster which is about to destroy us. Has science somehow become an evil thing? No. True science is a body of fact, and facts are not of themselves immoral. They become good or bad merely in the use to which we put them. The discovery of nuclear energy has brought the potential of enormous benefit to mankind. At the same time, it's given man the ability to destroy himself, to wipe out civilization. Now, which will it be? Well, frankly, I don't know. But this I know. The very formulas and facts which gave man the ability to blast himself into eternity, these very facts contain powerful moral and spiritual implications which just might keep him from doing it. Now, we've considered some weird and fantastic things. But the implications to which we have just referred are the strangest and the most fantastic of all. And once again, they involve this relationship between time and space. Would you like to see, with your own eyes, 1,000,000 years into the past and see it in the present, as though it were right now? Well, you can. Tonight, take a little drive out into the country, away from the city lights. If the night is clear, and if your eyesight is good, you will be able to see in the constellation of Andromeda a faint, hazy object. It's called the Andromeda Nebula. It's actually another universe, another galactic system, over 1 million light years out in space. While you're looking, remember this. The light reaching your eye tonight left that distant universe over 1 million years ago, and it has been traveling like a wailing banshee through space ever since. You're looking more than 1 million years into the past and seeing it as now. Where the nebula in Andromeda is, or how it looks right now, we can't know for sure. For all we know, it may not even exist. All we can know is how it looked over 1 million years ago. Now, of course, it isn't necessary to go this far into space to encounter the same principle. Every day as you look up at the sun, you're looking 8 1/4 minutes into the past, for the sun is 8 1/4 light minutes away from the Earth. Also at night, when you look up at Antares, you're seeing 250 years ago, just as though it were right now. From time to time, the newspapers report the discovery of a nova, or a supernova, a star that bursts into flame like a giant hydrogen bomb. Any astronomer knows that what we see as now actually happened hundreds or even thousands of years ago. Now, all of this is illustration of the fact that time and space are linked together. But what does this have to do with morality? Well, in the world today, wherever man accepts the concept of a supreme being or a creator of the universe, there are at least 3 points of general agreement. First, that God is omnipotent. That is, he is all-powerful. Well, he'd have to be to create the universe. Then, he is omniscient. That is, he is all-knowing. And he is omnipresent. That is, he is present or existent everywhere at once. Do you realize what this means? If time and space are inseparably linked together, then a God who is not limited in space cannot be limited by time. If to him every point in space is here, then every moment of time is now. Let's think for a moment about what this means. Let's say that you were not limited in space. If you were on the star Rigel looking back to the Earth, Joan of Arc would just now be rallying the people of France. On Betelgeuse, John Bunyan would be writing Pilgrim's Progress. And on the star Canopus, the gallant 600 would be charging half a league, half a league, half a league onward. And if you were on the star Sirius, you could see what you were doing 9 years ago, because you're still doing it. Gives you something to think about, doesn't it? You know, it's an important thing for us to recognize the possibility that every act, good or bad, lives on and on, that we are forever accountable for our actions. But responsibility is the stuff of which character is made. And accepting a full measure of responsibility is the highest challenge before any young person today.